Cyclopropane is not a normal compound. Its single bonds behave like an alkene. Cyclopropane breaks almost every bonding rule you've learned in textbooks, and today I'll show you why. Let's get started with the unique features of cyclopropane. The strain energy of 27.5 kilocalories per mole is the most important feature of cyclopropane, and it arises from two factors. The first one is related to the bond angle of 60 degrees. Normally, carbon atoms with sp3 hybridization have a bond angle of about 109 degrees, but in cyclopropane it's reduced to 60 degrees, leading to substantial ring strain. This strain energy is called Baeyer strain. The second strain energy comes from the steric clash between substituents of cyclopropane. As you see, the three substituents are in the same plane, resulting in an unfavorable eclipse conformation. This type of strain is called Pitzer strain. Because of this strain energy, cyclopropane has a tendency to release the tension. So, ring opening is a thermodynamically favorable process. You might think that strain energy is the only reason for the unusual reactivity of cyclopropane. Yes, it's an important factor, but it's not the whole story. We need a bonding model to describe what's actually happening in cyclopropane. Generally speaking, there are three models that describe the bonding in cyclopropane. The first one is the Coulson Moffitt model. Before going through this model, let's have a quick recall of sigma and pi bonds. This is a normal carbon-carbon single bond in an sp3 hybridization. As you see, the orbitals have a head-to-head interaction. This type of orbital interaction is called a sigma bond, which is a strong bond. In a pi bond, like ethylene, orbitals have side-to-side interaction. This interaction is not as strong as head-to-head interaction. And because of this weaker overlap, alkenes are considered reactive species. Now let's take a look at the carbon-carbon bond in cyclopropane. At first glance, you might think that this is a normal carbon-carbon bond in sp3 hybridization, and the two carbon atoms have head-to-head interaction. But that's not the case. Because of high ring strain, the orbitals are forced to be bent. You can think of it like a banana with a curved shape. Because of this similarity, carbon-carbon bonds in cyclopropane are known as banana bonds, in which orbitals are deviated about 22 degrees from a normal sigma bond with head-to-head interaction. When bonds are bent, the properties of the compound change. Now this is not a normal single bond because there is no direct head-to-head overlap for maximum interaction. These bent bonds are something between a pi bond with side-to-side interaction and a sigma bond with head-to-head interaction. Because of having this pi character, cyclopropane shows reactivity like alkenes that we don't expect for a single bond. For example, in reaction with HBr, it produces propyl bromide. The same reactivity is observed in propylene, which produces 2-bromopropane. As a result of bending, the pi character in the carbon-carbon bond increases. You might wonder, what is the hybridization of bent bonds? In classic Vesper theory, there are sp, sp2, and sp3 hybridizations, but we can't explain bent bond with Vesper theory. As a result of bending and increasing pi character of the carbon-carbon bond, it has unusual sp5 hybridization, obviously showing more pi character relative to sp3 hybridization. The second model for describing cyclopropane is Walsh Model, which is based on molecular orbital resulted from calculation. So it represents a more accurate picture of bonding in cyclopropane. For describing a molecular orbital of a sigma bond between two atoms, we use this diagram. As you see, as a result of linear combination of two atomic orbitals, there are two molecular orbitals with different energy. The lower molecular orbital is a bonding orbital and bonding electrons fill this orbital. The higher molecular orbital is an anti-bonding orbital. These orbitals are also different in shape. In the bonding molecular orbital, density of electrons is placed between the atoms. Having said that, in the anti-bonding molecular orbital, density of electrons is extended outside the bond. The orbital mixing is going to be more complicated when three atoms in a cyclic arrangement interact with each other. Calculations indicate molecular orbitals pattern in this system is 1 down and 2 up. It means that one orbital is created in the lowest level of energy and two degenerate orbitals in higher energy. Molecular orbitals in cyclopropane follow one down to up pattern. We build molecular orbitals by combining free CH2 groups positioned at the corners of a triangle. There are 3 carbon-carbon bonds, so 6 electrons fill these orbitals. In low-lying orbital, each of 3 CH2 groups use sp2-like orbitals. The orientation of orbitals may not be aligned with what you've learned in introductory organic chemistry. Interestingly, they are not along the carbon-carbon bond, they are pointing toward the center of the ring. In other words, density of electrons is placed at the surface of the ring instead of between atoms. This type of orbitals is called radial orbitals. For 2 degenerate orbitals, CH2 groups use their p orbitals. These p orbitals are called tangential orbitals because they are arranged in the periphery of the ring. Another important point is that each of the 2 degenerate orbitals has a node. One of them has a node exactly on the vertex of the triangle, so there is no p orbital, and another is placed on the edge between 2 carbon atoms. When it comes to reactivity, radial orbitals are not accessible because they have low energy. So tangential orbitals are responsible for reactivity of cyclopropane. They have pi character, and they are also the home orbital of cyclopropane. The third model for describing cyclopropane is Dewar Model. It may ruin all the things that you've learned from textbooks. You know that benzene is an aromatic compound. Based on Haeckel's rule, a compound is aromatic when it's planar, cyclic, and it has 4n plus 2 pi electrons. Benzene perfectly matches this rule because 3 planar pi bonds are conjugated together. Conjugation is a result of interaction of orbitals of pi bonds that are in the same phase. The Dewar model states that in cyclopropane, 6 sigma electrons of 3 carbon-carbon bonds are aromatic by Haeckel rule. I know that this doesn't make sense, that sigma bond creates an aromatic system, and visualizing this model sounds impossible based on classic organic chemistry, but based on the Dewar model, cyclopropane is the sigma aromaticity paradigm. We can explain some physical properties of cyclopropane by Dewar model. Hydrogens of cyclopropane have an unusual chemical shift of 0.22. This value indicates that these hydrogens are highly shielded because H-NMR chemical shift of cycloalkanes from cyclopentane to larger ring are quite similar, from 1.44 to 1.54. These unusual, highly shielded protons in cyclopropane are explained by aromatic-like ring current of sigma bonds. We can rationalize some physical and chemical properties of cyclopropane by the Dewar model, but this model is still under debate and some scientists are against the presence of sigma aromaticity. Let's summarize these models. The Coulson-Moffitt model sees the cyclopropane ring as a bent bonds that have partially pi character. The Walsh model states that homo-orbitals have pure p character, and these orbitals are responsible for high reactivity. Based on the Dewar model, sigma electrons of cyclopropane create an aromatic system. So here's an important question. Which of these models is correct? To be honest, this question is wrong, because all of these models are correct. This is not about true or false. All of these models see the cyclopropane ring from different angles. Most of the time, the Walsh diagram is used for explaining the behavior of cyclopropane in chemical reactions. In the rest of the video, I'm gonna go through how cyclopropane interact with other functional groups and explain it by the Walsh diagram. You know that the primary carbocation is not stable, but when it attaches to a double bond, it becomes a stable compound. The origin of this stability is the conjugation effect of the double bond. Let's see this conjugation effect in orbital interaction. Here are the pi orbitals of the pi bond conjugated with the empty p orbital of the carbocationic center. What happens is electrons from the filled pi orbitals move into the empty p orbital of the carbocation, leading to a stabilization. This interaction is possible because pi orbitals of the double bond and the empty p orbital of the carbocation are in the same phase, and they have suitable orientation for interaction. We show this orbital interaction by resonance structures, showing the localization of the positive charge. Now let's see what happens when a cyclopropane ring is attached to a carbocation. The first thing is that there are 2 possible orientations of the carbocation center relative to the cyclopropane ring. The first one is called the bisected conformation. Looking from the top shows that the carbocation bisects the carbon-carbon bond of the cyclopropane. By rotating the carbocation center, the second conformation is achieved, which is called the perpendicular conformation. Now it's time to see how cyclopropane interacts with the carbocation by Walsh orbitals. The homo-orbitals of the cyclopropane have two degenerate orbitals. Choosing which one contributes to the interaction depends on the condition and orientation of the ring, but most of the time this one is used for showing the interaction. Now let's go back to our case. In the bisected conformation, the Walsh orbital and the empty p orbital of the carbocation are in the same phase and they have suitable orientation for interaction. Just like the double bond, electrons move from the Walsh orbital to the empty carbocation center, leading to a stabilization. But in a perpendicular conformation, the situation is different. As you see, the Walsh orbital and the empty p orbital are perpendicular to each other, so they cannot interact. As a result, the bisected conformation is more stable than the perpendicular conformation. If you are interested in such orbital interactions, check out this video to gain a deeper understanding of this concept. I've put the link in the description. This conjugation between cyclopropane and the carbocation center is nicely reflected in the bond lengths of the cyclopropane. The bond length of cyclopropane is 1.50 angstrom. But when it conjugates with the carbocation, C1, C2 and C1, C3 bonds become longer and the C2, C3 bonds become shorter. How do you rationalize these changes in bond lengths? Let's have a closer look at Walsh orbitals. As you know, there is a node between C2 and C3 carbon atoms, so these two orbitals have no interaction. But the left lobe of the p orbital on C1 has a constructive interaction with the left lobe p orbital on C2. The same interaction occurs between the right lobe orbitals of C1 and C3. So electron density is placed between C1, C2 and C1, C3. In the bisected conformation, we found that the p orbital on C1 interacts with the carbocation, but in fact, electron density from C1, C2 and C1, C3 move into the carbocation center. In other words, it's not about only the single orbital on C1. When electrons are depleted between two atoms, the bond becomes weaker. The more a bond is weakened, the more elongated it becomes. This is the reason why these two bonds become longer upon conjugation. In chemical language, we show this interaction by this resonance form. The most important point is that C2-C3 has a double bond character in the resonance structure, which explains why this bond is shorter than a normal carbon-carbon bond in cyclopropane. Changing the length of the bond is not limited to carbocations. Any electron withdrawing group that can accept pi electrons from cyclopropane changes the bond length. For example, when two carboxylic acids are attached to the cyclopropane ring, C1, C2 and C1, C3 bonds become longer and the C2, C3 bonds become shorter. But the amount of change is less than that of carbocation. Understanding how substituents change the bond lengths of cyclopropane is crucial for reaction design. Isomerization of cycloheptatriene is a good example to understand the importance of this concept. Cycloheptatriene is in equilibrium with Norcaradiene. This is a pericyclic reaction and occurs with the help of pi electrons in cycloheptatriene. This equilibrium is shifted towards cycloheptatriene because there is an unfavorable ring strain in Norcaradiene. Now it's time to develop your critical thinking. Imagine you work in a lab and your supervisor asks you to find a way to shift this equilibrium toward Norcaradiene. How do you do this? As a hint, you can use any substituents on the cyclopropane ring. Pause the video and find a way. In the previous example, we found that pi acceptor substituents shorten this bond. When a bond is shorter, it becomes stronger. In Norcaradiene, this bond should be broken to convert to cycloheptatriene. So if you find a way to strengthen this bond, the breaking process becomes harder because it requires more energy. Installing pi acceptor substituents like a cyano group makes this bond stronger and shifts its equilibrium toward the Norcaradiene side. Until now, we used this Walsh orbital to show the orbital interaction between cyclopropane and acceptors, but this one also can be used for interaction. As a last example, let's see how it works. The donorability of cyclopropane is reflected in the rate of solvolysis of the Norbornane system. The rate of solvolysis of Norbornane is significantly increased in the presence of cyclopropane ring. In the solvolysis of Norbornane, a molecule of solvent is replaced with the leaving group. This is a transition state of this reaction in which the leaving group is departing from the molecule and positively charged carbon atom is forming. Every factor that stabilizes this positively charged carbon atom decreases the energy of transition state, leading to an increase in the rate of solvolysis. In our case, cyclopropane does this. Let's go to 3D space to see what's going on. Here I show the transition state. To simplify things, I remove the leaving group and only show the positively charged carbon atom with an empty p orbital that is forming in the transition state. There is a hidden interaction between the Walsh orbital of cyclopropane and the empty p orbital. I said hidden interaction because there is no direct bond between the carbocation center and the cyclopropane. As you see, the Walsh orbital of cyclopropane and the p orbital of carbocation are in the same phase and have constructive interaction. This leads to flow of electrons from the HOMO orbital of cyclopropane to the empty p orbital of the carbocation. This kind of interaction is called a through space interaction or remote effect, because there is no bond between the two interacting groups.